Hello, this is part 4 of my set of videos on steady state error. Picking up on the slide that I left off with in part 3, I talked about these three different inputs. A step input, which is very aggressive, a ramp input, which is a little bit less aggressive, and then a parabola is even less aggressive than that. But the expressions for these are given underneath here. UT stands for the unit step function. So UT, the way that it works is before t equals 0, it's 0. And then after t is equal to 0, it's 1. So we use actually the unit step input in all three it's used in all three expressions for the types of ramps with the types of inputs. With the ramp input, you have an extra t there, so as you can see, as t goes on, and this grows linearly with t. Before t is equal to 0 is 0. And the parabola is the same way, except the t is squared, so as time goes on, it increases at a parabolic rate, which is the name of the input. Now, when you take the Laplace transforms of this function here, so all I've done here is take the Laplace transform of RT to get into the algebraic domain, then the transfer function, well, it's a constant, so and the Laplace transform is linear, which means that you can pull the R0 out in front of it. So the Laplace transform of a constant times something is equal to the constant times the Laplace transform of that thing. So the Laplace transform of u of t is 1 over s. And so this is the expression for our step input. When you add an extra t in here, it actually adds an s on in the denominator of the Laplace transform of that input. So the ramp input, instead of being r0 over s, it's r over s squared, r0 over s squared. And then we have a t squared in the parabolic input, and that converts into r0 over s cubed in the for the parabolic input. Now, the practical way of thinking of these two is R0 is the size of the step. Okay, it's how much it jumps up. Here, R0 is actually the rate of increase. It's the slope of the ramp curve. And then increasing in complexity, here with the parabola, the R0 is the rate at which the rate of increase increases. Okay, you can think about that if you want to, but don't lose too much sleep over it. We're just learning how to use this here. And what we want to do is we want to see how each one of these inputs affect our system. So we're going to apply these to the system that we just looked at when we were looking at steady state error. Okay, so we'll start off with the step input. And what that means is these are the formulae that I had. Well, this is the formula that I worked out for ESS. Now here, with the step input, remember, if we go back and look, the Laplace transform of the step input is R0 over S. So we see that here. This is broken out into the pieces. And so what happens is that this extra S that we get from the final value theorem cancels out with the S that you get from the unit step input. And so we wind up with this expression right here. And what I've done is in the next step over here, I have broken GH into NGH over DGH. So this is the numerator of the open loop transfer function, G times H, and this is the denominator of G times H. Okay? Now, if we look at this, if DH, or DDH, so I'm just looking at the denominator here, goes to 0 as S goes to 0, then this value right here, this fraction here, goes to infinity. And if the fraction goes to infinity, This is a constant on top. We're adding 1 to infinity, which is infinity also. So this whole fraction here goes to 0, and that would mean that we would have steady state error. But what we would have to have for this denominator of the open loop transfer function to go to 0, so that this would go to infinity, it has to have an s, a lonely s I call it, or a free integrator, that's the other way to put it, in the denominator there. It has to be an s alone, so that it's a factor in there, so that the whole thing will go to 0, and that will go to infinity, and that will go to 0. You can't have a factor like s plus a or s squared plus a times s plus b. It has to be s alone. It could be an s times these other factors. That would work too, because if you had an s alone that went to 0, it would wipe everything else out in the denominator. But if all you have in the denominator are factors like this, the s goes to 0, but the a remains. Okay, so you have to have a free integrator in the denominator of the open loop transfer function for the steady state error to go to 0. All right, you may have to think about that for a while because it's a little bit complicated, but this is the kind of analysis that you need to do for each one of these cases. Okay, we've got 3 different types of input, and as we'll see in a second, we have 3 sort of common type open loop transfer functions we're going to look at also. Now let's look at the ramp input. I replaced the step input, which was R0 over S, with R0 over S squared. And then when that happens, one of the S's from the ramp wipes out the S from the final value theorem, and then I multiply that through, and I have an S here and I have an S here. Okay? Now, I apply my final value theorem to that, and I've broken, in the next step, I've broken the GH up into a numerator of G and a GH and a denominator of GH. And if I look at S going to 0, what happens with this S going to 0? It just goes away. But now we have this term here, and if we want 0's steady state error, this term plays no role in that. This is a constant. So if we want 0 steady state error, this is going to have to go to infinity. And for this to go to infinity, then S divided by, well, DH is going to have to go to 0, but you have this S up here. So for the S over DGH to go to infinity, as S goes to 0, DG has to now have 2 lonely S's in it. So I got to wind up with a lonely S in this fraction in the denominator if I want this to go to infinity, so that the whole thing can go to 0. So I have this extra S up here already from the ramp. I had 2 of them. And now I've got to have 2 S's in here, so that I have an S left over after I do the cancellation of this S, so that this can go to 0, this can go to infinity, this can go to 0. Okay, so it's a little complicated, and it gets more complicated as you keep adding more and more sophisticated inputs. You have to have more S's in the denominator of the open loop transfer function. Parabolic input is very much the same. I replaced the R0 with SQ, R0 over S, or R0 over S squared for the ramp, with R0 over S cubed, which is for the parabola. And we wind up really in the same position that we had before. Except when we do this cancellation here, I need to have 3 free integrators, 3 lonely S's in DG, so that this whole thing can, we're left with 1, so this can go to 0, this can go to infinity, and then the whole thing can go to 0. Okay, so it's just a little bit more complicated. All right, I think I'm going to stop here, yeah, and pick it up because I'm over 10 minutes. We'll pick it up in part 5.